Hello class, today we're going to identify the intermolecular forces experienced by molecules. First thing we need to review is a dipole. We talked about bond polarity, we talked about a difference between the electronegativity in atoms. A dipole is what occurs when an atom or a molecule has two poles, a partially positive side with electron deficiency and a partially negative side with electron excess. The larger a dipole, or in other words, the greater the electronegativity difference, and I'm using En to abbreviate that, electronegativity difference, the stronger the intermolecular forces will be. So, for instance, if we're using an electronegativity table and we look at the value for oxygen, which is 3.5, versus the value for hydrogen, which is 2.1, that is a difference of 1.4. That is a very strong dipole compared to C and H, where C has a value of 2.5 and H has a value of 2.1. That electronegativity difference is only 0.4. The bond with a stronger dipole or a larger dipole would be the OH bond when comparing C and H to OH. When we're talking about intermolecular forces, there are going to be three main types that we look at for covalent molecules. We're looking at London dispersion forces, or abbreviated LDF, first. London dispersion forces are the attraction between two atoms or molecules with temporary dipoles. The temporary dipoles are created by uneven distribution of electrons around the atom. This can occur in any atom or molecule. It is also generally considered the weakest intermolecular force, or IMF, compared to others, but the strength does increase with the size of the atom and the number of electrons it has. I do have a quick animation. So here's our electron cloud. The electron cloud is constantly moving and shifting within an atom. Because of this shifting, you sometimes get areas where there's more electron density and areas where there is more electron deficiency. Again, as we mentioned with our dipoles, the areas with deficiency are going to be positive or have a partial positive, and the areas with excess are going to have a partial negative. That just means more electrons exist where the negative ends are. As a result of these dipoles that you can see are temporary and moving, when we come in contact to other atoms who are also shifting and moving at the same time, we form these attractions between each other. These attractions are your London dispersion forces. The next type of intermolecular force is called dipole-dipole forces. So this is the permanent attraction between two molecules with permanent dipoles. Quite literally, the dipole of one molecule interacts with the dipole of another molecule, hence dipole-dipole. This only occurs between polar covalent molecules. When combined with the London dispersion forces, this results in a stronger attraction between molecules. The third type of intermolecular force that we're going to look at is called hydrogen bonding. In combination with London dispersion forces, it is the strongest type of intermolecular force. It occurs only in polar molecules, and they have to have a certain feature in the molecule. H must be bonded to an F, an O, or an N. So fluorine, oxygen, or nitrogen. Because fluorine, oxygen, and nitrogen are very electronegative, the molecules that have H bonding have very large dipoles. Hydrogen bonding is when H of one molecule interacts with the lone pair of F, O, or N on another molecule. So I know they didn't draw the lone pairs in here, but there are technically two lone pairs here, and they are forming an attraction with H because this H is a very large partial positive due to being bonded to a very large partial negative. So it is a stronger dipole. Essentially, hydrogen bonding is a dipole-dipole force, but it's much stronger, and so it gets its own classification. We also have ion-ion attraction. This is an electrostatic attraction between oppositely charged ions. You only see this in ionic solids or ionic compounds. And we know that ionic solids have a lattice structure. It's kind of like an alternating net or a weaving basket of parts that is very energetically favorable. This is the strongest attraction. It is stronger than all other intermolecular forces that we have talked about so far. Therefore, compounds that are ionic have much stronger bonds between each other than compounds that are covalent. This will impact our physical properties later on when we link the physical properties to the intermolecular forces that we see. As you can see with the scale, dispersion forces are relatively weak. Ion-ion forces are about 400 to 1,000 times stronger than dispersion forces. Something to keep in mind is that dipole-dipole forces are only strong when in combination with the dispersion forces. And again, every single atom has dispersion forces. When we're looking at something like water, the type of intermolecular forces it experiences can dictate whether or not it is solid, liquid, or gas. And it's based off of one, the temperature and the amount of energy the particles have, but also the interactions they have with each other, which we'll look at a little bit more in our next lesson. So let's work through some of these together. First thing we have to do is draw our Lewis structures. So I know I've got my 4 H's that I have to attach here, and I've got 4 single bonds for each. And that will create a tetrahedral shape. Now I know it's a tetrahedral shape because there are 4 bonds and no lone pairs on the center atom. When I look at my chart here, I can find that combination of 4 bonding sites on the central atom and 0 lone pairs. And I can find that that's a tetrahedral molecule shape. The next thing I would have to check is for the polarity. I know that 1, CH bonds are generally nonpolar because if I found the electronegativity difference, it'd be a difference of 0.4, which is less than 0.5. So since the CH bonds are nonpolar and I have all nonpolar bonds, I can assume that this is a nonpolar molecule. When I'm trying to identify the types of intermolecular forces, I have to kind of go through a systematic flow chart. We know if it's nonpolar, it can only experience London dispersion forces. When it's polar, we know we can have London dispersion forces and dipole-dipole. And then we also have to check to see if it qualifies for hydrogen bonding. So let's go through and draw the next one. I put my 3 H's on nitrogen. I see nitrogen does not have a complete octet, so I have to add in a lone pair. And then I have to check. I've got 3 bonding groups and 1 lone pair. That combination of 3 and 1, if I go back to my chart, 3 and 1, if I follow that across, is trigonal pyramidal. Now, there's 2 ways we can look at this. One, the NH bond, if you calculate the electronegativity difference, is considered polar. So if I were to draw dipoles, my arrows would all point towards the nitrogen. Since they're all pointing the same direction, I can assume it's polar. The other shortcut you can use is looking at whether or not the molecule is symmetrical. Because there is a lone pair on the central atom, I can never be symmetrical, and therefore I have to be polar. So if you see a lone pair on the center atom, that's a shortcut for figuring out if it's polar. I know this has to have London dispersion forces. And since it's polar, it also has to have dipole-dipole forces. I'm going to abbreviate that D-D. Now, I have to always check if I have dispersion forces and dipole-dipole, I have to check for hydrogen bonding. Ask yourself, is there an H in this molecule? The answer is yes. And is that H bonded to a nitrogen, an oxygen, or a fluorine? The answer in this case is yes. So this also experiences H bonding. Let's do a couple more. Here we can go through and draw CH3Cl. So when I draw CH3Cl, I know that the CH bonds are nonpolar, so I don't need to draw dipole arrows for that, but the CCl bond is polar. Remember that the bond dipole points towards the more electronegative atom. So since the arrow is pointing in one direction, this is definitely going to be a polar molecule. We can go back and identify the shape. There are 4 bonding groups and no lone pairs, so this is tetrahedral. Since it's polar, I know it has to have London dispersion forces, and I know it has to have dipole-dipole forces. Again, check. Is there an H in the compound? Yes. Is that H bonded to a nitrogen, oxygen, or fluorine? No. Since it's not bonded to one of those 3, it is not hydrogen bonding. It's just London dispersion force and dipole-dipole. You can go through and do the next few. I'm going to draw each of these. Now, water, be careful with water because water's shape, people tend to draw in a straight line, but it's really bent. If you draw it bent, like I have drawn it here, that will help you figure out its polarity a little bit easier. I see a lone pair on my central atom, so I know that that's going to be polar. And this is a trigonal pyramidal shape. And then I know I've got London dispersion forces and dipole-dipole because it's polar. I don't have any hydrogens, so I don't need to worry about hydrogen bonding. If I were to check the dipoles and go back, this is a good way to check yourself. The PF bond is polar, and they all point down towards the fluorine. So since they point away from the lone pair, they're pointing in the same direction. This is polar. The OH bond, as we discussed earlier, is definitely polar. And when I draw it this way, these do not cancel out. They point towards oxygen. So this is definitely polar for 2 reasons. 1, the dipoles do not cancel out because it is a bent molecule and not a linear molecule. 2, I have lone pairs on my central atom. So again, if it's polar, I've got LDF and dipole-dipole. And then ask yourself, is there an H? Yes. Is that H attached to an oxygen? Yes. Therefore, this also has H bonding. My last one, when I go through and draw, I know I end up having to get a triple bond with my nitrogen. This only has 1 bonding group, which confuses people sometimes, but since it's just 2 atoms, we can view it as linear. Since it's bonded to itself, we know that is a nonpolar bond. Nonpolar, so it is a nonpolar molecule. So the only thing it experiences is London dispersion forces. The last thing I want to do is just link strengths to these because that will help us with our next lesson sequence. It says, now that you've determined which IMFs are present in the 6 molecules above, rank them from weakest to strongest intermolecular forces. For molecules that have similar IMFs, take into account the total number of electrons the molecule has. Larger molecules have stronger London dispersion forces. So first thing we should do before even ranking them is just count how many electrons they have. And we can do that by looking at the atomic number, because the atomic number is equal to the protons, which is equal to the electrons. So carbon has an atomic number of 6. Each hydrogen has an atomic number of 4. So we have 10 electrons here. NH3 is 7 with an atomic number with 3 hydrogens. So the total is also 10 electrons. And then CH3Cl, you've got 6 for carbon plus 3 hydrogen. So that is 9 total, plus 17. So 17 plus 9 gets us 26 electrons. PF3, we know fluorine has 9 electrons each. So 9 times 7, 9 times 3 is 27. Plus 15 from the phosphorus. So then that leaves us at 42 electrons. H2O has 10 electrons, and then N2 also has 10 electrons. So those electrons will be important in a minute. First thing I know is that my London dispersion forces are going to be weakest. So if I'm trying to compare CH4 and N2, they're about the same in strength because of their number of electrons. They both have dispersion forces. I'm sorry, I made an error. Nitrogen's atomic number is 7. There should be 14 electrons here. So if we're ranking, the one with the fewest electrons would be the weakest. So this is LDF only. So that is the weakest because it has 10 electrons. It is weaker than N2, which is also LDF only, but N2 has more electrons. Then we can move on to our polar molecules with dipole-dipole only. If I'm comparing CH3Cl to PF3, this one has less electrons. Than PF3, which is 42 electrons. This one has LDF and dipole-dipole. This also has LDF and dipole-dipole. And then my last ranking, I'm running out of space here, I have to compare NH3 to water. This one is tough because they have the same number of electrons and they experience the same IMFs. If you run into an issue where it's the same number of electrons and the same types of intermolecular forces, you have to look at the strength of the dipole. The OH bond is going to be more polar than an NH bond. And for that reason, H2O will have the strongest intermolecular forces compared to NH3. That is all for this lesson. In the next lesson, we'll review this and talk about physical properties and the strengths of intermolecular forces.